Hello, wonderful people. Welcome to Cosmology Talks. Today we have Christoph Saulder, who is a postdoc at CASI, Jeongin Moon, who is a PhD student at MPA, and David Valcin, who is a postdoc at Ohio University. They're talking today about DESI, the Dark Energy Spectroscopic Instrument, and BAO, the Baryon Acoustic Oscillations. And finally, this is not a forecast or any non-actual data result paper from DESI. It's actual detection of the BAO. So this is very cool, as it shows we are now entering the next era of observational cosmology. DESI has measured BAO, Euclid's launching later this year. Rubin and Simon's observatories are both in construction. So yeah, observational cosmology is entering yet another very exciting era. So welcome everyone. Do you want to start by telling us briefly about your paper?
We did the first BAO detection from the initial 2 months DESI data and tested the DESI BAO analysis pipelines using unblinded data. So this work is the meaningful milestone to move on to DESI year 1 and year 5 data analysis.
Quick question, when can we expect the year 1 data analysis? I'm sure you're going to say it later, but it's probably the question that's on everyone's mind.
We are expecting the year 1 results will come out end of this year or the beginning of the next year.
Within a year, that's exciting. Awesome. And if people are thinking of this talk or your paper in 6 months, or when the DESI year 1 results are coming out, what would you want, if there were only 2 things they're able to remember, what would you want those 2 things to be?
I think if we have to remember only 2 things from this paper and this presentation is first, the results are amazing. After only 2 months of data collection, we are already as precise as BOSS, final data. It only gets better when we get to year 1 and even year 5 in the future. So stay tuned, and I think the results are going to be impressive. Yes.
Why did you do this? I suppose this is, given that you guys are the first people with actual DESI results, you can be excused the general intro into DESI and what it is and what it's doing and how it is pushing the boundaries of current observational cosmology, but then also specifically why your paper, why is it coming out now, and why aren't we waiting for the year 1 cosmology results to also include your paper?
Yeah, so among the many science goals of DESI, putting some constraint on the dark energy is a very important one. And one of the best probe of dark energy is the Baryon Acoustic Oscillation, or BAO. So I guess a bit of introduction for people who are not very familiar with the BAO is at the beginning of the universe, when you have the primordial plasma, you have the competing force of gravity and the radiation pressure of the photons that will create oscillation in this plasma. And this oscillation, that battle between gravity and radiation pressure, will create acoustic waves. And those acoustic waves will displace matter in concentric shells and create a pattern and distribution of matter, if you want, at this epoch. And as the universe cools down, the pressure drops, and the universe expands, then the photon will be free to leave this plasma and travel freely inside the universe. And this baryonic pattern, the baryonic oscillation, will be frozen in the universe. The matter now, as it won't have to scatter with the radiation, will be free to fall inside the potential well, and the overdensity already created by dark matter that was allowed to collapse earlier in the universe. And this typical concentric shell, this isotropic shell in the universe, will create some density peaks if you look at the distribution of the galaxies in the sky later. So you can see on the bottom image here an idea of this acoustic peak, big similar if you throw a rock in a pond and you have these constructive and destructive interferences. So this is the familiar pattern for some of the people. So now, if you fast forward to nowadays, you will see that as the universe expands and evolves, the theory of the universe and the expanding universe will make some prediction about the distance scale, the typical distance between 2 galaxies, the most probable one, given the distance that this acoustic wave that was able to travel at the time. So you can see that the value is more or less 150 megaparsecs or 100 megaparsecs average. And you can infer and put some constraint on this value if you look at the CMB, the cosmic microwave background. But an alternative way of probe this oscillation pattern is to look at the large-scale structure of the universe. So as I said, if you do a 3D map of the universe, if you do some survey spectroscopic, if you look at redshift or photometric, and in our case, we use a spectra. And you have different estimates from previous survey here, SDSS, when you have this BAO distance slider, and as a comparison with the BAO estimate from Planck, which is the CMB-based estimate, and you have the line of 1 as a function of redshift. If you look at different redshifts, you usually have to look at different traces. So what we call traces is different types of galaxies, because they have different properties that you can infer. The typical way on how we infer the constraint on this dark energy and this distance scale is we compare the expected value of the ruler predicted by the theory with the value we get from doing the survey and the different clustering properties of the galaxies. But the theory is mainly linear up to a point, but if you get to our epoch to these days, you will have some small scale effects, so that we call non-linearities. And the idea is you need to remove those effects to have the most accurate prediction on this distance scale, and that we call BAO reconstruction. Basically, you move back the particle in time to their initial position, and you remove those non-linearities. And that you can see in the plot here if you start for the top left panel. And you have, for example, you can really see on the left side of each panel when you have this little peak of distribution that it's not perfectly, because the baryonic oscillations are supposed to be isotropic. So there's no preferred scale in 3 dimensions. But here you can see that there's a preferred dimension. And when you do this reconstruction, you remove some of these anisotropies. You get a better estimate of it. So that's what we want to do. And it's because this oscillation pattern is proportional to the evolution of the universe. So you can put constraint on the Hubble, so which is very interesting this day in the Hubble tension, and also on the angular diameter distance, whether you look along the line of sight, so radially, or across the line of sight. You can put constraint on different quantities.
So to do this reconstruction, you obviously have to know where the gravitational wells are, or like what direction the galaxies were moving in. Is that reconstructed using other DESI or using DESI data, saying there are more galaxies here, therefore there was an overdensity, therefore things were falling towards it, or is it reconstructed in some other way?
No, it's a good question. So usually what you do is you use this Zeldovich approximation, and you say that the displacement is proportional to the potential well and the velocity field, because if you have an overdensity, you will attract faster, and then you have this velocity displacement that you can correct. You don't need external value, you just need to assume that this continuity equation is valid, and you just move particles back in time, more or less. The only assumption after you have other from smaller scale, when you can account for the damping and also the smoothing scale, when you remove the impact of these non-linearities. But just to correct the location of the peak, you don't need external data set on your value. You just only use your sample, your original sample.
Right, but you do need to estimate the density wells, right? Because otherwise you can't just move the particle back with its current velocity. I mean, in an in-body simulation you could, because you know its velocity, but in an observation you certainly don't know its angular velocity, and along the line of sight you don't know what is redshift and what is peculiar velocity. So there must be some density field estimation going on.
Exactly. So basically you start from the position, whatever you want, either 3D Cartesian or rate extension declination. You're right, you create a delta field when you have over density of your map, and then you correct as a function of over or under density in your distribution. Yes.
And we measure this BAO using DESI. DESI stands for Dark Energy Spectroscopic Instrument, and it's currently 2 years into its 5-year mission to take spectra nobody has seen before and explore the galaxy and distribution in ways we haven't done before yet. So it aims to get redshift, so distances, for 35 million galaxies over an area covering about 1/4 of the sky. And before DESI, before a spectroscopic part started, there was a photometric survey called the DESI Legacy Imaging Survey. Year 9 was the latest release before the start. That was used for target selection because it's a multi-object fiber spectrograph and we have to know where to point the fibers. We can't just point them randomly at the sky and hope to get some spectra of something, but we are a little bit more informed. We know where there's a galaxy and that's where we point them. And as mentioned, it's a multi-object fiber spectrograph, so it can take 5,000 spectra in one exposure, and the fibers are automatically positioned using robots.
Is this 5,000 spectra in one exposure thing like new to DESI? Was Sloan doing that as well, or could it only take one at a time, or?
Sloan also did many exposures at the same time, but 5,000 is a new unprecedented number. I think for Sloan it was a few hundred. I would have to look this up. I'm not 100% certain what it was exactly. And also the automatic fiber positioners. So here at the focal plane, you see there are 5,000 tiny robots that can rearrange in any shape within some small radius around for each fiber. While in SDSS, for example, they had a physical focal plane and they had to drill holes into it. So each exposure had to be manually prepared in advance and somebody had to stuck in the fiber. So even if from one exposure to the next, somebody had to change this physically. I mean, they prepared the plates in advance, of course, for one night, but then somebody had to go there and plug in the fibers again. And this we don't have to do, so we can go from one exposure to the next exposure within like a minute or two. Just the robots have to reconfigure the focal plane. And this focal plane has like this petal-like shape with 10 petals, we call them. Each of them has 500 fibers by itself. And then it feeds it to a fiber spectrograph, where it will be spread out into 3 different arms covering optical to near infrared, and we can take very high quality spectra of like many objects at the same time.
Can I just ask maybe a dumb question? And I think you did answer it. I'm just making sure I understood it correctly. So when DESI, the instrument, points at a particular patch of the sky, the fibers within DESI also have to be arranged to be pointing at the individual galaxies. Is that right? That there's like a very small range where the light coming in will go down from the light from each individual galaxy will go down each individual fiber, and that has to be kind of fine-tuned.
Yes, those are the robots that move the fibers around. And of course, during the geometry, there's one slight downside. We can't put any fiber to every place. So all fibers have like a small area where they can move around. That's the range. So if there's a cluster, we have to visit the same patch multiple times to get all the spectra we want. While some spectra will, if there's like a really empty area, we have sometimes empty fibers that will just observe the sky, but that's useful for calibrations as well. As we have different, as DESI aims for a large redshift range, we have different tracers. So the nearest galaxies are the bright galaxy survey. They go up to a redshift of 0.5. And since those galaxies are intrinsically very bright, it's essentially a magnitude limited sample. We can observe it during bright conditions or bright time conditions. So DESI has 2 observing conditions. It's split into bright time and dark time. Bright time is usually around sunset, when there's still a little bit of light in the sky, or when the full moon or moon is up. And dark time is really the perfect observing condition where we observe the targets which are a little bit harder to observe, and we need better conditions to do so in a reasonable amount of time. And those are, for example, the luminous red galaxies, LRGs. As the name says, they are luminous and red, and they can be found between a redshift range of 0.4 and 1.1. And then to higher redshift, we have emission line galaxies between 0.8 and 1.6, also observed during dark time. And for the highest redshift ranges up to 3.5, we have quasars, so quasi-stellar objects. Those are like AGNs or something very bright in the center of a galaxy, so usually supermassive black holes accreting stuff, and this is really, really bright, so we can see it's very far into the universe and still get a spectra from which we get the redshift. Additionally, another main tracer, also it's not used for BSO, is the Milky Way science objects. So those are local stars that can also be observed during bright time. Some people are very interested in those. For our current project, it's not relevant, but there are many projects within DESI, and some focus on those as well.
A local star, is that something in the Milky Way?
Yes, Milky Way or Milky Way halo or dwarf galaxies, and yeah. And as we said, when we have the fiber arrangement, we have to visit every patch multiple times. So in bright time, there will be 4 passes. Those tiles are not overlapping, so for effective coverage, each spot on the sky will be visited at least 3 times. While in dark time, we have 7 passes, which will count to for effective 5-time visits of every spot on the sky to get the most spectra possible.
Right, and are these 4 samples, are these things that we should get used to, that in even DESI year 5, it'll be the BGS, the LRG kind of samples that everyone's going to be doing cosmology on?
Yes, those are the main tracers. They are a little bit supplemented by secondary targets, but those are the ones that what the instrument was designed for, and those are the highest priority ones that will be observed. And then on lower priorities, there are other targets as well for other science cases.
Can I ask a kind of funny question that you might not know the answer to, but maybe you do? The emission line galaxies have this kind of second bump at almost redshift 0. Do you know what caused that? That kind of just looks a bit funny. It's just, maybe there's an interesting story behind it.
I think it's just a target selection. So emission line galaxies are usually late type galaxies, so spiral galaxies, and that we can still see some emission lines. So usually with the LRGs, we can still see the full continuum of the spectra. While for emission line galaxies, mostly continuum is lost in the noise, but we see some of the strong emission lines. While also the way they selected is like a series of color cuts. And these might also target nearby spirals, I think, or nearby small galaxies that fall into this.
Okay, but for some reason at, say, redshift 0.5, there's a deficit before it goes back up again. Okay.
This is the range it was designed for, and the other one is, I think, a side product of the target selection. And those histogram there was just for the first 2 months of observation. So essentially the base data we are using now. And it will expand largely when we get to year 5. Yeah, and this just shows where the main tracers are located in a slightly different way. And the important thing is these emission line galaxies are in the time period when dark energy becomes dominant. And this is where we want to explore with DESI the expansion rate very well. So we have lots of targets there, and it also shows the distribution in numbers. So we have mostly emission line galaxies, but still lots of bright galaxies and luminous red galaxies, and also a real large sample of quasars. So we have more quasars than SDSS has spectra in total. So it will be a massive sample, and yeah, it will be impressive.
So what was the kind of maximum redshift that SDSS got to?
So SDSS has the same kind of tracer categories. It has like the main galaxy sample, which is essentially similar to our BGS sample. The luminous red galaxy sample, it has like a LRG release, an ELG release, and a quasar set, and so it's using the same classifications, but we are targeting for more targets for fainter galaxies and just also a larger area in space.
Cool. Well, yeah, for the first, at least on this channel, the first intro to DESI when there are actually results. That's awesome. So now, what was the specific work that the 3 of you, although I guess 3 of you and collaborators who aren't here at the moment, did to measure the BAO in this? Was it 2 or 3 month sample?
So the purpose of our work was to see if we can detect BAO with initial 2 months of DESI observation, and to test the BAO analysis pipelines, including correlation function measurement, weighting scheme, covariance matrix, reconstruction, BAO fitting. And also we did the feature forecast for DESI year 5 data based on 2 months observation results.
So can I just clarify something? Christoph said that your BAO detection is already comparable to say the boss, I guess, from Sloan, and that was not with 1 year but with 2 months worth of DESI data. Wow, that's really
impressive. So yeah, as I mentioned, as we already talked, we used the first 2 months of observations, which were observed from May 17 to July 9, 2021. We used the 342 bright time tiles and 304 dark time tiles. We used the data sets which are unblinded to test BAO pipelines for these specific data sets, but the rest of main survey will be blinded. And for these specific data sets, we only focused on LRG and BGS bright with luminosity cut because they show the best completeness and the number densities. So these are the correlation function measurements from the 4 DESI tracers. You can see in the figure the 2-point correlation functions of each tracer with the jackknife error bars. And the dashed line shows the simple damped linear theories. You can see that BGS and LRG show really clear BAO peaks, but not for the ELG and QSO for this specific data set. So you can see that the reason that we focus on BGS and LRG for this work. And also for these measurements, we used PyCore code in Cosmology package. In the Cosmology package, you can see many useful packages for BAO analysis. So if you're interested, please check this GitHub link.
So I know that these data points are usually heavily correlated with each other, but should I be getting worried that the BGS at large distances kind of just drops off and that the LRG seems to have a second bump at about 160, or is that not statistically significant and my chi-squared by I is...
The dashed line is only the linear theory, so these are not actually fits for the BAO. And yeah, we will see how it will go for the year one, but I don't think this is the statistical errors for the measurements.
So essentially you're saying I shouldn't be reading into the fact that there looks to be a second bump in the LRG and a complete drop off in the BGS? That's...
Yeah.
But if I may add, on top of what Jeongin says, on the BGS, when you have this drop, it's due to the bin correlation, so it's expected. But it's because we had to put a magnitude cut on the BGS, so we decrease the sample size, because otherwise you have a large variation of redshift distribution on the redshift slice we select. So we put this flux limitation, so with more samples, and it should correct also this effect of bin correlation for the BGS.
Okay, and the LRG second bump, is that...
I think you have some of this effect, with more samples.
I'll keep my eye out and see if I can see it in the 1 year data.
On the year one, yes. So as Jeongin said, we have this data from the first 2 months, but since we only have one universe, you want to have an account of the dispersion on the error if you're going to do the fit. And also you want to create this covariance matrix and the different matrices. So usually you resort to mocks. Either we have this Abacus suite, which is made from n-body simulation on 2 gigaparsec boxes. And we have 25 of them when you populate your galaxy using a HUD model. And we have also EasyMox, 1,000 of them, based on the extended Zeldovich approximation. And both of them are what we refer to cut sky mocks. It's where you use a cubic mocks and you apply the survey geometry and you displace the particle, because you can use a natural evolution, the redshift evolution of your box, and this is what we call the light cone box, but the cut sky one could be cubic box that were displaced given the Abacus cosmology. So it's like artificially displaced in redshift. And that's the two different type of suites we're using.
So this extended Zeldovich, I think one of you mentioned earlier, I think it might have even been you, David, that the Zeldovich approximation is where you kind of take the particles and move them along the trajectory they started on, and that's okay at getting some quasi-linear stuff, because essentially, I guess my way of thinking about it is it's because of inertia, that later forces don't undo the kind of inertia of where the particles are going. What is the extended Zeldovich approximation?
I put this in. It's just an extended version of the formalism. That's how it's called in the EasyMock paper.
Okay. Is it like just the second order where they move on parabolas instead of straight lines, or?
I assume there's some additional term in it. I think I've not worked with the details of the mocks, so I'm not creating them. Yeah.
Then the idea is to calibrate the mocks to make them the most accurate possible, closer to the actual data set. So in order to do so, you need to apply the different systematics that will impact the data. And for example, the redshift failure, the target selection, the problem for imaging. You have also to apply the similar redshift range and so on. And to do so, we apply a succession of different masks to the mocks. The first was to reproduce the survey geometry and the footprint of the data that Jeongin showed in a previous slide. So you have the dark time and bright time, as Christoph introduced earlier. Then you have also this effect of randomness that you will get from the imaging problem that might occur. And also the final one is problem of completeness, because when you observe, you have different patches of the sky, but you have priorities in your observation. So first you will observe quasars in bright time, then LRG, then ELG. But if you only observe only once this patch of the skies, you won't observe LRG and ELG, and then your completeness will drop, and you don't have the expected amount of galaxy that you will have with several passes of observation that you will get for the year 1 or the year 5 later. So you have to also introduce this randomness selection in your mocks, and that we did by subsampling based on some pixel probabilities. But we realized that when we were about to create this covariance matrix from the calibrated mocks, that the mocks were created with an earlier catalog. So we have a slight shift in amplitude, especially at large scale, with our DESI M2 sample compared to the HV3 that was used before. So we decided to instead use a semi-analytical covariance matrix made with Rascal C. The code that was developed by Oliver Philcox and used for us with Misha Wachkowski in Harvard. So Rascal C is a mix of semi-analytical and semi-empirical covariance matrix in a way that you use an input two-point correlation function and some random catalog to calibrate your covariance, and then from the two-point correlation function you also use jackknives that are a sub-region of your space to calibrate the short noise, and you account for this Gaussian, you do some Gaussian marginalization, and you correct the short noise, and it will give you this covariance estimate. Because the idea from the analytical part is you can reproduce this two-point correlation function with some integral or some sum of function, and then when you do this, you apply this empirical part when you need some easy mocks for the calibration. But instead of using 1000 easy mocks, for example, you can only use one correlation function and 60 jackknives. That's what we use in the paper, and this is much more computationally efficient compared to the easy mocks that you can do before. 60
jackknives meaning 60 different subsamples of the
60 splits, yes, exactly. 60 splits of your space on your region. So that's what we tested here, because to be sure that we could trust this semi-empirical analytical covariance, we did a test where we computed a covariance from the easy mocks and one from Rascal C based on the easy mocks, and we did a BAO fit for the two different type of mocks, Abacus and easy mocks, that you can see here. And this is for the LRG samples. And on the top row, this is pre-recon, so when the non-linearities were not corrected, and the bottom part is post-recon, when you correct for the non-linearities. And the first column is detection significance. So how many sigma can you find a BAO signal? The second one is the alpha parameter, because when you do this BAO fit, you have a template, and you need to rescale the location of your peak by this alpha sigma. One is no rescaling, so you can see here the value. And also you have the sigma, the error on the best fit. And you can see that the agreement between the two covariance type is excellent, because the black line is x equal to y, and the scatter is very limited around this line. So you can trust, basically, you can see that the Rascal C is in a very good agreement with this easy mock covariance type.
And each one of these data points is one of these jackknife mocks?
No, sorry, it's one realization of the mocks. So we have 25 Abacus and 1000 easy mocks, yes.
And these mocks are supposed to be representing our universe. I guess what I'm wondering is that the detection significance kind of ranges from 1 up to 6 or even 7. I think what I'm wondering is, could our universe have been an unlucky universe where the detection significance of the BAO was actually just 1 or 2 sigma? Or is that kind of a very unlikely universe?
Basically, if you look at the stars on the plot, that gives you the mean significance value. So you expect some scatter around it. I think the main concern, if you look at the significance, and do I have outliers? Do I have like mocks that are so bad that they completely differ from the rest? And here, even if you have a scatter, then you say that they're more or less consistent between the easy mocks and the Abacus one. and the central value is close to what's expected.
Oh yeah, and yeah, the central value is close to like 4 sigma, which is. I mean, I guess my question is just the same as any measurement that the Hubble tension. One could say, well, okay, it's 5 sigma, but it could just be a 5 sigma outlier. Like we could have had a universe where the BAO was only detected at 1 sigma, but that would itself be an extremely rare universe. So.
Yes, that you can see like your data are completely at odds with your simulation. Then you can ask question. Either you don't know the systematics or we're missing something.
This is also the individual mock BAO research, but to test the BAO reconstruction efficiency. So for these figures, the x-axis show the pre-reconstruction BAO research, and the y-axis show the post-reconstruction BAO research. So for this case, we also included the data points in the figures in significance and sigma alpha figures, but except the alpha figure because we decided to blind our cosmology for this stage. So in this work, we don't really show the alpha values of data BAO research. And you can see in the figures that the data show really high significance and low sigma alpha. And the reconstruction really does improve significance and decrease sigma alpha. If you see the stars of the MOX, which show the mean values of the MOX.
So the mean values were slightly better post reconstruction, but I guess our universe just happened to be a sort of on the edge of that bubble. And
yeah, so we are kind of lucky case. So this is one of our main research in this work. The left panel shows the 2-point correlation function of energy with and without reconstruction, and the solid lines show their fits. The right panel shows the BAO significance. We could get the 5 sigma BAO detection and 1.6% precision using around 260,000 energies. And this result is really remarkable because we could already get from initial 2 months observation the consistent BAO precision with the BOSS DR9, which is 1.6 precision. And this is the BAO detection from the BGS bright. We could get the 3 sigma BAO detection with 2.6% precision using around 110,000 BGS bright with luminosity cut. And you can see also the precision is quite comparable to BOSS DR12 result.
Lines here, are they like a theoretical fit or like a fit from the MOX or?
Yeah, if I may, yeah, it's the BAO fit, the best fit when you use a template, when you split with a smooth power spectrum, no BAO signal, and you add 1 BAO power spectrum with the damping terms, and you do this fit when you have 5 free parameters.
Okay, I guess this answers my question from earlier, and that this dip is actually expected by the model. Although I see in this one here that my second peak, you can see it just sneaking in on the far right of the plot, but because the original one here went all the way out to 200 megaparsecs in the LRGs, and you see my postulated second bump, and in here you've cut it off, but it looks like it's still there and probably not expected by the solid line.
Yeah, actually we didn't focus on that ranges, so we only focused on the BAO ranges. So yeah, our fitting range was 150 megaparsec per H, so we didn't focus on the bigger separations.
I can still add something on this bigger separation. So from other BO work, I know the larger the separation rate, the more sensitive you are towards systematics. So if there's something in a mask, if there's something in our weighting scheme, if there is like we reach the size of the tiles and it gets messier the larger you go. So I have one data set in a different paper that's in preparation where we had the issue of, there was one part in the mask missing and it totally messes up the larger scales. I
see. So what you're essentially saying is this bump at 160 megaparsecs could be statistically significant, but could be detecting the mask or the survey geometry, or
it could be errors with the survey geometry, with the weighting schemes. You get more extremely sensitive towards all kinds of messy systematics in the larger scales.
I won't write my my anomaly paper just yet. Then I'll hold off.
Yes. So the for a Fisher forecast, we compared the covariance matrices for the M2 sample and the year 5 sample, and did a rescaling using the best fit from the actual data. So instead of just like models, we had data, and we have covariance matrices for the full year 5 and the sample of the first 2 months. And we found that there will be an improvement of a factor of 5.8 for the final year 5 sample compared to what we have over the entire BO range. So down on the bottom, I have like an example from the simulations. Those would be on the left side, we have the error bars from the first 2 months, what we expect. And on the right side, it's how it will look like after 5 years. So it's clearly visible that we will improve significantly when we have the full data set in a few years.
Wow. And if there's even if there's like some fine-grained features to the BAO from some, I don't know, primordial model or something, it would be showing up, which would be really cool.
Yes, so there will be opportunities to distinguish several models once we have the final data. So to sum up, DESI is now the first stage 5 cosmological experiment that is producing data and has been producing data now for almost 2 years. And in this paper, we showed that we were successful in testing the pipeline that will be used for the main data analysis. There's still some improvements and we learned things for it, but we have a working pipeline. We know what to do now, and we have tried it and it works. And even with the very early data, so just 2 months of observations, we can already detect the BO in 2 tracers, like the luminous red galaxies and the BGS at high significance, so 5 and 3 sigma significance respectively. And thereby we proved that indeed we didn't oversell DESI. We can achieve sub% precision for the year 5 data, and it's on track and doing well.
Looking forward to the cosmology talk in 5 years' time or 4 years' time. Oh, actually, no, the 5-year data might be even, because you said it's been taking data for 2 years, so it might be.
Yeah, it will be 5 years from now, roughly. I think we might get faster with the analysis the further we progress, but that's speculation.
Cool. Well, yeah, that's very cool and exciting. And I guess you've shown us already what we should expect from the 5-year data, and maybe on a shorter time frame as well. What can we expect? When can we? Well, you've said when we can expect the year 1 data, but what can we expect in it, and what else is coming in the near future for you guys personally, and also for DESI, and then also what the rest of the cosmology community should be waiting for.
So concerning DESI, the thing that will come out very soon is the early data release. So this is data collected before the main survey, so it doesn't even have the first 2 months, which we analyzed in it. And so it was just for testing, commissioning, validations, and stuff like this. And this will come out this summer, so in a few months' time from now. And then we are all working on year 1 data that was collected between May 2021 and June 2022. And it's in progress. We already have like 50 million reliable redshifts for this range. And as we said, the expected release is end of this year, maybe early next year. Depends on once the papers are done. And yeah, we learned lots of things for further optimization. And it will contain the first true cosmological results. So with actually alpha values and not blinded alphas as we provided. And currently DESI is collecting data for year 3, and it's at the moment, I just checked, we are slightly ahead of schedule, and we have already covered 44% of the dark time observations and 65% of the bright time observations that were initially planned. And DESI will be the most competitive BO experiments for the decade, and we are looking forward to many discoveries.
So yeah, the last question, what work being done in cosmology at the moment do you think is particularly underappreciated by the rest of the community?
I think I would say because I work partly on the mock calibration, so I have a slight idea about all this pipeline reduction, and I think all the people that work with, we are part of the paper when we have the first detection, the data, some cosmological analysis, even though it's still the cosmology is blinding and still impressive to show the significance. But all the people that took part in the data reduction before, when you need to look at the different spectra to make sure that the fit are correct, you're detecting the right type of galaxies, then you need to infer all this ungrateful work about all the systematic, the imaging problem that occur, the fiber assignment. I think it's a bit less shiny, but it's very important for us to trust the data when we do the analysis.
So I might be biased, but I think a little bit peculiar velocity science is slightly underappreciated in cosmology, at least when you compare it to BAO, lensing, time domain, and supernova and CMB. It's important stuff, and I'm working also on the DESI peculiar velocity survey, so that's why I might be biased in this regard, but it can help to improve the constraints we get from BAO at very small, in the very local universe, so like redshift 0.1 and lower.
Well, we will have a plenary speaker on peculiar velocities at Cosmology from Home this year, so if anyone else agrees with Christoph that peculiar velocities are important, then come to Cosmology from Home. Awesome. Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos, and click like to help with YouTube algorithms, both for yourself and for the channel, because YouTube will know to recommend more stuff like this to you, and share the channel with colleagues. If you have any questions or suggestions, leave a comment. Otherwise check out what talk. There's nothing else on DESI on the channel, is there? Could go all the way back to EBOS. Otherwise check out, I think, Eva Maria Mueller's talk from 2020, which was the kind of last big EBOS release, which is the closest we'll get to DESI until DESI results come out in the future. And sign up for Cosmology from Home as well, which has now got open registration at cosmologyfromhome.com/registration. Other than that, thanks Christoph, Jeongin, and David for the great talk.
Thank you.
Thanks. Bye.
Thank you.